So everything from here on will be recorded. And as I said, from pretty much day one of this class, you can keep track of, like if you think, there's a topic that you might need to go back to revisit, jotting down the time mark of that topic can be very helpful. So you don't have to re-watch the entire recording of the lecture, just the portion that you need. Alright, so it is time. I'm going to get started with the class. And we'll start with the lab from yesterday. Let's see, this is the one from yesterday. Alright, so do you guys want me to go over the entire thing, or just one of the questions, particularly what we are seeing on the screen right now? Actually, I take it back. That's not. Nope, that's it. This is correct. Okay. Eric is typing on the keyboard. The whole lab. Okay, we can do the whole lab. Alright, so question number one. So a lot of this really is a repetition of what I talked about in class already. TTP, text story processor, has no actual stack pointer. This statement is kind of important because in some architectures there are registers that are specifically for that are designated as stack pointers. So they only work with special instructions like push, pop, call, and return. But in TTP, there's no such thing. So all four registers, A, B, C, and D, are pretty much equivalent in all instructions. So as a result, the so-called concept of a stack is really completely artificial. It is basically just based on how we utilize register D as a stack pointer, and that is just a convention. But we're going to use the same common convention for the entire class. So I don't want people to tell me that. But I like to use register B as the stack pointer. So we're going to use register D as the stack pointer. There are many ways to implement a stack, but the use of an array and a stack pointer is one of the most efficient way to do it. There are two operations related to the stack. There's push, there's pop. The convention of using register D as the stack pointer also means that register D points to the next item to be retrieved, and the most recently item pushed is pointed to by register D. That's bad grammar there. The most recently pushed item is pointed to by register D. So just flip these two words, pushed versus item. Which of the following instruction mnemonic retrieves but does not remove an item from the stack into register A? Oh, this is not the lab? Okay, so let me see. The lab from yesterday is parameter and return value. There we go. Okay, Eric is correct. Alright, so let's do this one. Alright, so this one sets most return value of red subroutines are scalars, such as integers, addresses, and etc. These are all small size with a fixed width. As such, scalar return values are usually passed to the caller of a subroutine via a register. Most compilers have a convention of which register to use to specify the return value of a subroutine. So in this class, using TTP, we use register A as a convention. So this is why, a subroutine that looks like this in C is going to look like this in TTP, ASM. It is important to understand that a single return statement in C has two operations. The first one is to specify the return value, and then it actually continue execution in the caller. Given this is how a return value is specified, what is the value of register B after the following code executes? Assuming 5 is as defined above, which is here, try to answer this question by analyzing the code and not running it through the simulator. And here's the code. Alright, so this is question number 1. Oh. Yep, okay. Alright, so what you need to do is to track what is in the stack at any time of the execution of this program. So this is the initialization of the stack pointer, which means the stack pointer is just 1 byte beyond the last memory location of RAM. And then these 3 instructions together is pushing the return address of the first call onto the stack. And then we continue execution to 5. In other words, these 4 instructions together is simply calling 5. So when 5 is done, it's going to return to this point. So when it returns to this point, we decrement D, which means we are reserving 1 more byte on the stack, and then we are storing the return value of the first call of 5 to that location on the stack. In other words, if I just execute this code, location FF is going to be storing 5. And then I proceed to perform the second call. So when you look at these 4 instructions, they look exactly the same as these 4 instructions, except for the return label is different. So in this case, we have return label 1, and in this case, we have return label 2. So it's going to perform another invocation of 5, which means by the time we get to this point here, which is when the subroutine returns to the caller, register A will have 5 in it because that's the return value of the second invocation of 5. But at the same time, the stack pointer is still pointing to whatever we stored earlier, which is from this particular ST instruction. So that's why, this particular instruction, load BD, is going to retrieve that byte that we stored earlier at location 255 or FF in hexadecimal, which is also 5. So A is 5, B is also 5. When we perform add BA, we are adding 5 to 5 and storing the result back into B. And that's why when this is all done, by the time we get to the halt instruction, register B is going to have a value of 10. All right. So next question. Question number 2. All right. Yes. I'm waiting for the question. The correct answer was 0. I don't think that is the case. I think the correct answer is 10. Well, let me submit and grade it so I can see. Alright, so let's scroll all the way to the end. Yeah, I think it should be 10. So we'll submit quiz. Yeah, it's going to complain about me not answering some of the other questions. Alrighty, so it did give me 1 point out of 1, so 10 is the correct answer. So there we go. And then in question number 2, while most return values are scalar, there are only 1 per invocation. The number of parameters vary widely, and so on and so forth. So this one is about parameters. Alright, so let me take a look at the text channel. And yeah, it's probably mistakenly accepting 0 also as a correct answer. So I had multiple keys, and it's not supposed to accept 0 as a correct answer. But I'm not going to take that point out, okay? So don't worry about that. But it should be 10. Yep, okay, all right. So we're moving on to question number 2. So question number 2 basically just describes how we pass arguments as parameters to a called function, and in this case is asking in the previous code at the entry point of subroutine XYZ, which means we are at the first instruction of XYZ, where is the argument 5 relative to the location pointed to by register D? Relative to the position. Okay, so indicate the offset in number of bytes where argument 5 is compared to where D is pointing to. So we have to observe the caller's code in this case. So the first thing we did was to push 5. So that's the first thing we push. The second thing we push is the return address. And then we perform the JMPI instruction. So that means when we are at XYZ, at the entry point of XYZ, register D is pointing to the return address, and the 5 is just 1 byte above that. So the correct answer in this case should be just 1 for question number 2. And then for question number 3, arguments are pushed on stack by the caller. How does a subroutine being called access them? So this is from the perspective of the subroutine. The relative position of parameters compared to the location pointed to by the stack pointer stays constant. In other words, the stack pointer is how we get back to the parameters. So this statement is really kind of important because it means even in the case of a recursion, for each invocation of a subroutine, the relative distance in terms of the number of bytes between where the stack pointer points to and where the arguments are located, where the parameters are located, stays constant. So, and then we move on and talk about, let us consider the example from the previous question. The caller code is like this. In the subroutine XYZ, right at the entry point of the subroutine, what does SP point to? So the last thing that we push before we do the JMPI to XYZ is the return address. So the correct answer in this case should be the return address. So the correct answer should be this one, the return address. All right, moving on to question number 4. Again, refer to the caller code as follows. Okay, this is the caller code. Let's say subroutine XYZ is defined as this in C. Okay, it simply returns whatever parameter is passed to it. What value should we fill in the following TTP ASM code to implement this subroutine? So the part to fill in is right here. So in order to figure out what that underscore 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 should be, we have to look at how A is being utilized. So after we do LDIA, we add D, which is the stack pointer, to A. So we're adding the stack pointer to whatever value that we have put into A through the LDI instruction. And then this is the most crucial part because we are using register A at that point as a pointer. And in the text here, this specifies the return value. So we want this instruction here to load the correct value into register A as the return value. In the C code, we are returning the value of X, which means after this instruction, register A should have the value of X, which is not at where the stack pointer is pointing to. It is 1 byte above where the stack pointer points to. So in order for this to happen, the underscore 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 needs to be exactly 1. So 1 should be the answer to this question. All right, so I'm getting some. Okay, there we go. Why would we add AD if we will just add load AA? Because the actual location of the parameter is relative to the stack pointer. In other words, what we put when we put a 1 in place of underscore underscore underscore, that is specifying the offset, not the absolute location. It's an offset from where the stack pointer points to. This is also why you're going through the trace is going to be helpful, because you can actually see where the parameter is actually stored in memory, and you can also see what the value of the stack pointer is at that point. And you can also see how the add instruction ends up computing the address of the parameter, and then so that the next instruction, which is the load instruction, would successfully get the value instead of the address of the parameter into register A. So all of this should be visually, shown when we actually perform the trace. All right. So question number 5. In the case of multiple parameters, the first parameter is pushed last. Consider the following C code. We have a subroutine that passes 2, 3, and 4 as arguments. So 4 is pushed first, and then 3, and then a 2, and then we push the return address, and then we call the subroutine. When accessed from the called subroutine, how does the address of the first parameter relate to the address of the last parameter? So because we pushed the last parameter first, it is going to have the highest address, and then the second parameter would be 1 byte below that, and then the first parameter is the first argument, I should say, would have the lowest address amongst the three. So let's check out these alternatives. The address of the first parameter is greater than, nope. The address of the first parameter equals to the, nope. The address of the first parameter is less than the address of the last parameter. Yes, that would be the correct answer. But just to be sure, the relationship between the address of the parameters cannot be determined by the caller code. That would not be true. So the correct answer is the third answer in this case. All right, moving on to the last question, I think. Refer to the code in the previous question, repeat it here so that you don't actually have to go back and look at the previous question. Assume the C prototype of sub1 is as follows. So we have A, B, and C all being unsigned 8-bit integers. And sub1 is now consider the subroutine sub1 code as follows. Okay, we load a 2 into A, and then we do an add AD. What is register A right after the add instruction? In other words, what is, exactly that's what it's asking. Okay, what is register A? What is the value of register A right after the add instruction? So what we know is register D points to the return address. D plus 1 is the first parameter. So D plus 2 is going to be the second parameter. Second parameter being B in this case. But it is not the value of B, it is the address of B, because we have not done the LD instruction to actually get the value of the parameter that is sitting on the stack. Okay, so let's look at the possible answers. The address of parameter A, nope. The value of parameter A, nope. The value of parameter B, nope. The return address, nope. It will be the last one, the address of parameter B, or in C notation, it is ampersand B. So there you go. Okay, so I have just gone over all of the questions in the previous lab. Are we okay at this point? All right, I'm not seeing any text activities at this point, so I'm gonna assume things are okay. And as such, I will continue with something that's new for today's lab. So today's lab is broken into two halves. The first half is kind of like this, with all the multiple choice or fill in the blank kind of question. The second part is a program that you have to turn in. So I do understand, within 80 minutes, it may be pushed a little bit to actually finish writing the program. So as a result, the program is not going to be due today. I will make it due next Tuesday, right before class, because next Monday is exam 2. So I will make it due next Tuesday, right before class starts, which is 5:30 p.m. The multiple choice and fill in the blanks part is going to be due tonight at 8:20 p.m. So it's broken up into two halves. Personally, I would just if I had time, to work on the program, I would probably try to finish it tonight. But if you don't have time, then you actually have basically the whole weekend, plus the one day between the second exam and next Tuesday. So you have one more day, to do that, beyond the weekend. So there we go. All right. So what I'll do next is switch back to my text terminal. I just got past it. Okay, I realized there's text activity in. Is there a lab on Monday? That is an interesting question. I don't think I can put a lab on Monday, so there'll be no lab on Monday per se. But since you guys, some of you may be still working on the program that I'm going to assign today, so I'll be online to answer questions if there are any on Monday after the exam. All right. So what we'll do now is we're going to take a look at a C subroutine. So we'll just kind of check out how comfortable people are with strings and pointers. So we'll go ahead and try to implement. Let's do string length first, okay? And we're going to do the C version first. So string length. Okay, let me just kind of show you what string length does. Okay. So this is the man page of string length. Unfortunately, it doesn't. The pager didn't work within Vim. So let me get out here and then man string length. There we go. Alright, so string length is calculating the length of a string, which in C and C++ is merely an array of chars, and it's going to be terminated by a no character at the end. So it returns a size underscore t, which typically is some kind of an integer, type, and then it has as its parameter, it has s, which is a pointer to a const char, because we are not supposed to change the content of the string. We are only supposed to scan it and find out, how long it is. And the length is supposed to exclude the null terminator at the end of the string. All right. So do we have any questions about what string length does? All right. If there are no questions, then we're going to move on into the implementation of this in C. As usual, I'm going to pound include stdint.h, and I'm going to implement a very special version of string length, where it can only measure length in up to 255 characters, because we are returning an unsigned integer that only has 8 bits. So we have string length, and probably be better off to call it text string length, because we don't want it to accidentally confuse it with the actual string length. I don't think it will, but it doesn't hurt to change the name a little bit. And in here we have const char star. I usually call it ptr, pointer. All right. So now we have to think about the implementation of this. Most people are now thinking, we can use a while loop to do this. The answer is, yeah, we could. We could use a while loop to do it, but that would be boring. So let's not do something that is boring, and instead we'll use recursion to do this. So we're going to use a single return statement. There's no other statement. There's no if then else. It's just return. Okay. So when you think about recursion, the first thing you have to think about is, when do we stop the recursion? Okay, when do we say, okay, enough? We have the answer right now. There's no need to perform further recursion. So in this case, it is when ptr is pointing to a null character, and this is how we check whether ptr is pointing to a null character or not. If it is returning, if ptr is pointing to a null character, that means whatever string is that I'm supposed to find the length of has a length of 0, because the pointer is pointing to a null character right away. So I'm just going to return a 0 in this case. So the else to this ternary expression is going to handle the case of, what if ptr is not null? Well, that guarantees that you have at least one character, right? The length is at least 1. So you say 1, but we don't know what the rest of the string looks like. So what we're going to do is we just say, well, let's treat the rest of the string as a string itself, and then we're going to call a subroutine to find out the length of the rest of that string. So this is how recursion comes in handy, because it works really well when you have some kind of a data structure where you can take one part of it so that it becomes a subproblem. just like in this case, because in this case the original string passed to a particular invocation of text string length is the entire string. However, I can always look at that as long as the first char is not a null. I can always look at it as, okay, we got one char, okay, and the rest is a substring. Let's go ahead and just say that the length of my original string is 1, because what I'm looking at right now is a non-null character. And then the rest of the string, I have no idea how long it is. I'm just going to call a subroutine to find out how long the rest of the string is. But guess who I'm going to call? It's not the ghost busters. It is going to be the same function. Okay, so that is how recursion works. And yes, I am teaching you guys, about the concept of recursion, even though you don't really need to know that in assembly language programming. But in your other classes, if you're taking 430, if you're going to take 440, the concept of recursion is super duper important. All right, so now we're also going to introduce the concept of local variables. Okay, so in this case, I have a local variable x that belongs to main, and we're going to say x equals to text string length of, let's pass a literal string this time. So we'll just say, recursion, exclamation point. There we go. And then return 0 at the end. All right, so this is the C version of the code. Now, if you're not 100% sure how this works in C and C++, you can use GDB and set up breakpoints, to examine, the like PTR up here to find out, how PTR is going to change when we perform the recursive calls. But our focus in this class is not how to construct recursive subroutines, because I will create the subroutines for you and specify those subroutines in C or in C++. Your job is to convert it into assembly code. Okay, so now our focus is how do we convert this into assembly code. So this program is going to illustrate a few concepts, and I'm going to use the right-hand side window to implement the same program but in TTP-ASM. All right, so first thing is we're going to start with a no op instruction, because I want this program to be traceable using the command line version of tracing the using the simulator to trace execution in the processor. So next thing we need to do is the usual stuff. Let's initialize the stack pointer, and this time I'm going to go back to the old way of doing things, which is the obvious way, and then JMP to main to continue execution in main. We have text string length here, and then we have main over here. Main is going to stop with a halt instruction. All right, so now we have the basic template of the function. And let's see where we want to start. I'm going to start with main. Okay, so I'm going to start with main here. So in main, the first thing we need to do is to allocate space for the local variable. Can someone kind of guess where the local variable is going to live? Knowing that local variables, there's one version of the local variable per invocation. So when in the case of recursion, every single invocation in the recursion has its own copy of the local variable. Yep, the stack is correct. D is the stack pointer, so it's not exactly right, but I think what Paul meant was it's on the stack, because the D is the stack pointer. All right, so let's go ahead and check out how we can allocate a byte on the stack, but without putting a value into it, because the way I do it in C did not put a initial value into X. This is it. That's it. This is how we reserve a byte on the stack so that we can have the local variable X in main. That's it. I mean, that's kind of cool. So what I'll also do is I'm going to start to use labels, so that instead of having to keep track of where the local variables or where the parameter is on the stack, I'm going to use a symbolic name. So I'm going to say main underscore x to make sure that this label is it's applied to local variable x of main. And I'm just going to put a 0 here because it is at an offset of 0 from where the stack pointer is pointing to. Because main is basically just a subroutine. The only thing that is special about main is it doesn't have a return address. It doesn't go back to anyone. But it can have local variables just like all other subroutines. So after this instruction, then the label would be effective at this point. So from this point on, I can use the label main underscore x to represent the offset from where the stack pointer points to local variable x. But I really don't have to worry too much about it until I'm done with calling text string length. And now I have to pass the address of a literal string. So now the question is, well, first of all, how do we make a literal string in assembly code? There are a few ways to do it. I'm just thinking, what would be a better way to do it. Let's do it, using the more obvious way. Okay. So what we'll do is we're going to use some space in RAM, and we'll just call this literal string 1. So literal string 1 is just a label, and I start this label definition using an underscore to emphasize that it is a name that we only use in assembly code. It is not present in C code, because in C code there's no need to use a label like this. So after that, we use a whole bunch of byte lines, and each one to only define one character of recursion. So the way we do this, unfortunately, it doesn't understand quotes, so that is not going to work. So we're going to have to do it the painful way, which is to look up the ASCII table. And instead of bringing up the ASCII table on the screen that you can see, I'm just going to bring it up off screen so that I can do the lookup really quickly, and so that you don't have to kind of get confused by that portion. All right, so lowercase r has a ASCII code of 114. Lowercase e has an ASCII code of 101. So you can see this is going to be a pretty boring process. Okay, so lowercase u is 117. Lowercase, you get the idea, right? So we have r is 114. S is right after, so which is 115. I is 105. O is 111. And then N is 110. And then we have an exclamation point. So exclamation point being a punctuation has a lower value, which is 33 in this case. And then we have the null terminator here. So that is actually how C compilers would do it too. A C compiler would actually look at a literal string and define those individual bytes, put it somewhere in RAM that is actually initialized to begin with, and then it would use an internal label that you cannot see in your C code, and then so that you can refer to it over here. So now we need to push that address on the stack. So we are not pushing these characters on the stack, we're pushing the address of these bytes on the stack. So to do that, we're loading A with the label itself, and then we just push it. So decrement D, ST, D, A. So that's the only argument that we need to push. Now we can push the return address. And that is done by LDIA .6 plus. I explained that yesterday why what .6 plus means. So if you're wondering what that means, you might want to refer to the lecture from yesterday. Same thing after that, just decrement d std a. So now we have the argument pushed, we have the return address pushed. It is time to continue execution in the subroutine, which is tax string length. There we go. And then when it comes back, the first thing I need to do is to clean up after the arguments, because the argument that is still sitting on the stack is not needed anymore. So we'll do that using an increment d instruction. And now that the stack is balanced, we need to store whatever is in register A into local variable X. So to do that, I could just kind of depend on my head, my brain, my mind to remember that X is where the stack pointer is pointing to at this point. I could do that. But if there are multiple local variables, then it might get a little bit difficult to remember which one is where. So instead of doing that, I'm going to use the other approach. Now I have to remember that I cannot use register A at this point, because register A has the return value of text string length. So I can use register B, I can use register C, both are usable at this point. I'm just going to use register B. And I'm loading the value of the label main underscore X into register B, and then do an add BD. Because main underscore X as a label is defined to be the offset from where the stack pointer points to the thing that I want, which is local variable X in this case. So by itself, it is not an address. I have to add the value of the stack pointer to the offset in order to get the address of the local variable X. So now that B is the address of local variable X, a simple st instruction to B from A is going to store the return value into X. And at this point, I'm pretty much done, except I'm going to do an increment D, because at this point, which is equivalent to the end of the subroutine, the increment D is deallocating the local variable itself, because in order for the stack pointer to be balanced, that needs to be done. So any questions about main at this point? All right, I'm not seeing any questions. Well, if you do have questions, go ahead and put it into the text channel. I will definitely answer those questions as they pop up. All right, so now we get to the trickier one, which is text string length, which is a recursive subroutine. So let's figure out what we need to do in this case. First thing first, we need to get to PTR first, and then we need to dereference it, and then we need to check whether it's null or not. Those are the first few things that we need to do. But instead of doing that right away, I'm going to use the same approach. Okay, so I'm going to use TSL, for text string length, as a prefix, and we have our parameter called PTR. So now I want to know, where it is supposed to be on the stack relative to where the stack pointer is pointing to. So it's helpful to draw a map of what the stack should look like at this point. So we have PTR pushed first, and then we have the return address pushed second, and the stack pointer is pointing to the very last thing that we push on the stack by the caller. So the stack pointer is pointing to return address. So that means the pointer itself, PTR, is 1 byte away from where the stack pointer points to. So I'm going to define it as 1. And that's really the lazy way of doing it, but for now it's going to be okay. And now we can go ahead and implement the code. Now, label definitions do not appear as opcode, because they're really not specifying any instruction. They do not get represented in the object code whatsoever. They are merely concepts that make it easier for us as programmers to define labels, utilize labels, so that we don't have to remember all kinds of numbers in our head. All right, so first thing first, we need to get to PTR, we need to get to pointer. So first thing is to do LDI A, and then we have text string length underscore PTR. So right after this instruction, register A has the offset of PTR as a parameter from where the stack pointer is pointing to. So once again, it is not an address until we add the stack pointer to the offset. So now register A is the address of PTR. The address of PTR is great, but it's not what we want because we want the value of PTR. So we need an LD first. So LDAA. At this point, we have the value of PTR. The value of PTR itself is a pointer, and we need to dereference it because we have this dereference symbol over here. But I notice that I might need to refer to the value of PTR down the line over here. So I'm going to save myself some trouble and put the value of what PTR is pointing to into register B. So at this point, you probably want to make a note somewhere that register A has the value of PTR, register B has the value of what PTR points to. Okay, so that is really important. But when we run this code, and look at the trace analyzer, everything's going to be more clear. All right, so now that we have the content or the memory location, the value of the memory location that PTR points to, now we can see if it is null or not. So I'm going to use the little shortcut thing that we have been using, which is using the AND operation where both operands are the same register. So all this does is to push the value of register B through the ALU so that we have a chance to set or clear the Z flag, which is the 0 flag, or the sign flag, and I shouldn't say or, and also the sign flag. In this case, we only care about the Z flag because we just want to know whether it is a null byte or not. So if it is a null byte, we need to go to the then portion of the ternary expression. So we'll just say this is going to TSL then. And you notice how I use TSL as a prefix for all the labels that are applicable only to the subroutine. So this way I don't have to worry about, I'm not really sure whether the then label has been used somewhere else in the program or not, because now the then label is only, this particular label is specific to the subroutine TSL. So that makes it easier to manage labels, although the labels do get a little bit longer. So now I'm going to define TSL then over here. What if it doesn't branch to TSL then? So that means we're going to supposed to go to the else case of the ternary expression. So we have a JMPI, a unconditional branch to TSL underscore else. Now, if you are asking, is there a more elegant way to handle this? The answer is yes. There's a more elegant way to do this, but it will basically you have to flip the ordering of these two statements, which is okay. But in order to preserve the order of the then versus the else value in the ternary expression in the assembly code, I'm just going to do this so that it is actually going to be the same kind of code. Now, right at the end of the then branch, you need a JMPI, an unconditional branch, to TSL end if, because otherwise it's going to continue execution in the else branch, which is not what a if then else statement is supposed to do. So this is where the end if is. Okay, so now I have just created the control structure for if then else. The then portion is the easy one. Okay, we just have to return the value of 0, which means we just need to say LDI A0. That's it. Okay, because that will specify a return value of 0. The else case is the one that is more complicated because now we have to perform the recursive call and then add 1 to the return value of the recursive call and then call that my own return value. Okay, so let's break down the steps, right? Before we can call recursively, we have to supply the we have to push the argument. So the argument is PTR plus 1, but fortunately we already have PTR in register A. So that means I can now do an increment A, so that register A is now PTR plus 1, and then we just push it on the stack, which is decrement D, STDA. And then once we have the argument pushed on the stack, we just have to push the return address. So we're going to do a LDI A dot 6 plus decrement D st DA. So that's going to push the return address on the stack, and now we can continue execution at the subroutine that we're calling. And then you're going to say, but which subroutine are we calling? The same subroutine that we're in. It doesn't matter, okay? The way we call a subroutine does not do anything differently in the case of a recursion. That is really important to remember, okay? So we go through exactly the same steps when we are calling recursively. When the recursion is done, which means execution will continue at where the cursor is, which is right here. We have the return value, but the first thing we need to do is to remember to deallocate the local variable. Excuse me, take it back. To deallocate the argument that is currently on the stack, which is ptr plus 1. So we take it off of the stack right now. And now register A has the return value of text string length, the recursive call. We just have to add 1 to it, which means I have to do an increment A, and that would be the return value. We're all done here. So that will fall through to TSL and if, which is corresponding to the actual and of what we need to do after this entire expression is evaluated, and the value is now in register A. So all we need to do now is to continue execution in the caller. So at this point, the stack pointer should be quote-unquote balanced, which means it should be once again pointing to the return address. So an LDBD is going to retrieve the return address from the stack. Increment D is going to deallocate the return address because it is now consumed, it's now utilized. And then JMPB to continue execution in the caller, and that should be the end of text string length. All right, so let me just kind of pause here and see if there are any questions about the implementation in TTP-ASM, or whether there are questions about the C code itself. All right, I am not seeing any questions. All right. Well, the good thing is everything is being recorded. So there is that. All right, so I'm going to exit and then use the script, okay, to run this code, or to assemble, simulate, and do the trace analysis. So this is string length dot ttp asm. Alright, so something doesn't work here. Argument list too long. Well, I haven't seen this error before. Okay, let's go ahead and check and see if it is done correctly. And we'll check source code, make sure that the source code is reflecting the program. So we do have text string length here, so that looks right. No errors, whatsoever. And then we get to RAM file, that looks good. And then we go to analysis. That is way too short. Okay, we should be seeing a lot more than this. And then we go to trace raw data. And trace raw data is longer, but it's still not nearly as long as it should be. Okay, so the script kind of messed up something along the way. I suspect that the trace is too long and it didn't quite finish. So let me do let me check first. So we'll check the TSV file and see how long it is. It's only 4.6 kilobytes, but it doesn't. Oh, okay. So wget doesn't want to upload anything that big. Okay, so that script is not. It's useful, but it's only useful up to a certain point, because I think once it is getting past 4 kilobytes, it doesn't want to do it in that particular way. Okay, I'm gonna have to figure out a different way to do this, but that's okay because we can always upload the TSV file directly into the trace raw data tab. So that's what we're gonna do now. We go to the trace raw data tab and then go to file, and then we say import and then go to upload, and we want to go to the subfolder called river spider, and in there is the string length.tsv file, which is down here. So double click it. Alright, so now we want to go through the process of specifying that we are replacing the current sheet. We want to use tab as a separator and do not convert in the import data. So doing this manually is always an option. Alright, and it's going to take a little bit of time to do the analysis, and this one is going to be a little bit longer than the other one because it doesn't go through the log compactor to compact the trace. So it's just going to look a little bit longer. Alright, so how do we know whether this program works or not? Okay, so that's the next question. So to answer that question, we're going to go back to the code. We're going to go back to the C code and also the assembly code. So this is -o and str length ttpasm. Alright, so what we want to do is to look at the C code. You can actually run the C code and find out what the value of x is right before the return instruction. So that's one way to do it. But what we want to do is also to find out where x is supposed to be on the stack, because in this way we can also find out whether we store the return value correctly on the stack or not. So this is where it is helpful to use a spreadsheet of some kind. Okay, so I'm going to just use a spreadsheet locally, because it's a little bit faster to run LibreOffice Calc locally on my screen than to go through Google Sheet in the cloud. And I'm just going through a bunch of dialog boxes off screen because I didn't save some of the files, and LibreOffice is asking me, do you want to retrieve those files, and so on. Alright, so what we want to do is to look at memory locations. This is location 255, 254, 253, 252, 251. Okay, I cannot count, so since I cannot count, I'm gonna cheat. So I'm gonna use the spreadsheet to help me do the calculation of these memory locations. Okay, I think we got enough locations now. Maybe not. Some more. There we go. Alright, so column A is reflecting memory locations. 255 is FF. This is where local variable x is. So column B is going to be saying this is the local variable x of main. It is located here. What about the next location? The next location is going to be the address of the string. Now, where's the address of the string? We can always find that out by using the assembler. Go to the Assemble tab and scroll down until we see the definition of the string, which is right here. So we know that in hexadecimal, the string is located, it starts at location 33 in hexadecimal. Okay, so we switch back to this and say it is at location 33, and The next location is going to be the return address to main. Return address to main. So that would form the first, what I would say, a call frame, because it is a chunk of memory that is what a subroutine needs in order to execute. So the first invocation is going to say, let me check what the pointer is pointing to, which is location 33. And location 33 in hexadecimal is not null, so it's going to do the recursive call. So when it performs the recursive call, it's going to decrement this address by 1, then push it on the stack, and now we have the return address to the function itself. So I'm going to use TSL to indicate this is text string length. If this is too small, which looks a little small to me, I'm going to bump it up a little bit so it's easy to read like that. Okay, so what about next? So next time it is going to look at location 32, and it will say, is that a null character? Oh, I take it back, sorry, I take it back. It's supposed to increment, not decrement. So it would be the next location, which is 34, and that is also not null. So now it will move on to 35, and it's going to use the return address to text string length again. And location 35 is also not a null location, because we have to do this all the way to 3D. Okay, so that means it's going to take up quite a few locations to get this done. So we have 36, 37, 38, 39. Should not have I should not have used a long string like this. 3A, 3B, 3C, and finally we have 3D. And then we have the return address for each one of these, because every time you call a subroutine, you need to specify the return address. And because these are recursive and there's only one point of recursion in the subroutine, so all of these are going to be the same, because they all have the same return address to the previous invocation. When it gets to here, the code in the subroutine will look at the location 3D and find that location 3D has a null character. It is at that point that the recursion is going to stop, and it will start to return. And when it returns to the previous invocation, it will take the return value, add 1 to it, and then use it as its own return value, and then keep going back. So going forward, it's going to do this. And then when you look at the return value from the subroutine, this invocation is going to return a 0. This invocation will return a 1. This invocation returns a 2. This will return a 4. And then we have 5, 6, whoops, and then 7, and then 8, and then 9. And then finally, when it gets to main, it should return 10. So we can do this. We can count, right? Recursion, RECURSION, exclamation point, 10 characters exactly. So by the time it returns to main, it would have a return value of 10 stored in register A, and also only at that point that the local variable in main is going to be updated to a value of 10. So column C is not what we're going to store at these locations, because the return value is specified in register A. So column C is indicating what the value of register A should be when the subroutine returns to the previous invocation. Alright, so that's what the stack is supposed to look like. So when you look at it from the hexadecimal perspective, we have to get all the way down to location 233. And let's see what that looks like in hexadecimal. So I think there's a dec2 hex. Yep, there we go. And we want to convert 233 into hexadecimal, and it is supposed to be E9. So we can look through the trace. We are supposed to go all the way down to location E9 before the recursion stops, and then it will start to go back up again. the stack pointer that is, it's going to go back up again, and eventually we should store a value of 10, which is 0A in hexadecimal into location FF. So that is what I think the program should do. And when you're debugging a program, which you're going to do quite a bit for the next 2 weeks or so, that is what you need to do too, is to figure out, on a piece of paper or using a spreadsheet, what the program is supposed to do. And then you go back to the trace analyzer and see how much of what you're expecting is matching the actual trace. That is how you're going to debug your program. So let's go back to the analysis of the trace. And this is going to be a long one too. So there are several ways to utilize a Google Sheet. So one thing we can do is we can actually track the stack pointer and find out when it got down to E9. So to do that, we can highlight the column. We go to Edit, and then we click on Find and Replace. And we can search for that exact string, which is D equals to E9. And I think it's uppercase. Oh, there we go. So uppercase E9, and then click on Find. And here we go. All right, so I claim that the stack pointer should not decrease any further after this. Instead, it will go back up again. So we got E9, keep going, keep going. So this is where it specifies the return value when A gets the value of 0, 0. You can also check the address of whatever instruction is doing this. It is at location 0F. So if you are to go back to the Assemble tab and go to that same location, which I have forgotten already, 0F. So when you go to location 0F in the code, which is indicated by column W, so 0F is right here. This is indeed the instruction that we use to specify a return value of 0. So this is a comforting feeling, okay? Because everything kind of matches out. It works kind of as expected. But when we keep going, we can see how the stack pointer is going back up again. Okay, it's going back up to EA, and then EB, and then register A becomes 0, 1, and then keep going up again. So register D is now EC, ED. The reason why it's incremented twice is because the first increment is from the subroutine itself, and then the second increment is from the caller. The first increment is to deallocate the return address. The second increment is to deallocate the argument that is still sitting on the stack. And then after that, register A is incremented to 2, and so on. Keep going, keep going, keep going. And at some point, D should become FF, and then we store 0A into FF. So keep going a little more. Come on, there we go. So at this point, the stack is back to main. Okay, I shouldn't say the stack, but execution is now back to main, and we have just deallocated the argument, which is the pointer to the literal string in main. And then after that, we should be storing the value into that location. So there we go. So we can see that 0A, which is the return value from the subroutine from main's perspective, is now stored to location FF, which is where it's supposed to go. And this last increment of D to 0, 0 is to deallocate the local variable itself, so that the stack is now completely balanced back to its initial value of 0. Phew. Okay, so this is what I mean when I said the trace analyzer is going to be helpful, but it's only going to be helpful if you can create a picture of some kind. You can hand draw this picture, you can use a spreadsheet, you can do whatever you want, but the idea is you need to know what is supposed to happen on the stack, what is supposed to be, what are the return values, and so on, so that you can verify, using the trace analyzer to track whether the program is doing what you think it should be doing. So if you see something that is different, then you have to ask, is my expectation wrong, or is the program itself wrong? Okay, and because it can be either one or both, right? So, but either way, this is how I would imagine that most of you should be writing your code, is to utilize the trace analyzer to help you out. So I'm going to stop talking a little bit and see if you guys have any questions. All right. I am not seeing any questions. I'm going to give you guys a little bit more time to think about the question because I'm going to take row. So let's see. Let's go back to a screen here. So here's row taking. Today's row taking word is pointer. That is an interesting question. The question is, well, not question, but the comment was, so pretty much we need the tracer for the rest of the class. Let me specify the date of the row taking activity, and then I'll get back to that question, because it's going to be a longer type of answer. We'll specify this to be 6. Oh, what the heck. I'll give you guys 6:42. There we go. Save and publish. So go ahead and do the row taking thing. The word of row taking is pointer. It is on the text channel of Discord already. Just copy and paste. All right, so let me address that comment of, so pretty much we need the tracer for the rest of the class. Strictly speaking, it is not needed. But in a practical sense, I would say it would be almost impossible to write code correctly and debug a program without using the tracer. In previous semesters, I have had, okay, I'm going to turn on the webcam just so that you guys can see my expression. All right, so in previous semesters, there had been people complaining and say that, requiring us to debug a program is unreasonable because that was not part of the description of this class. The description of this class never mentions anything about debugging. And I was just, when I received that comment, I was going like, okay, so we're supposed to be doing programming, and the inclusion of debugging techniques, both in the assignment, the lab activities, and also in the final exam, is not supposed to be there. And I cannot make the connection. I cannot understand why someone would expect teaching a class like this would exclude debugging techniques, because I think it is actually very, very important to learn how to debug a program, because that's what you're going to spend, unless you're, okay, assuming you're becoming a developer or a software engineer, you'll be spending a lot of time debugging programs. And a lot of times it's not even your code. It's code written by someone else, possibly a long time ago, okay, depending on what organization you work for. If you work for the state government, for instance, okay, and you work for a department like Franchise Tax Board or the EDD or DMV, they have legacy code that came all the way from the 60s, okay, in COBOL. There's no way you can actually find the original programmer to ask anything. So if your task is to debug, a particular program, or to write some new code, but then there are bugs involved, you still have to debug the program, okay? And I understand this is not something that other classes focus on. Like when you took CISP360, you might not have been exposed to GDB or other debugging tools and or techniques. Okay, but I think that is really crucial to get those concepts in as early as possible, because as you move on to additional classes like CISP 400, 430, okay, and these are considered lower division classes from the perspective of a 4-year university. If you check out the catalog of UC Berkeley, UC Davis, most of the UCs, most of the CSUs, they do not have anything equivalent to our CISP 300 or CISP 360. They start right away with CISP 400. And that is going to be their expectation, is you already know how to write code effectively, and in order to write code effectively, you have to know how to debug code. So that is my super long, response to the comment of, so pretty much we need the tracer for the rest of the class. The answer is, practically speaking, yes. I do not know. I don't teach CISP 400. I only know that CISP 400, well, I taught it once, okay? I taught it once because the professor who was assigned to teach that class became interim dean of the entire division for 1 or 2 semesters. So like 3 days before class started, they just said, "Hey, Jack, can you teach this class for Dave?" I go like, "Yeah, I understand object-oriented programming. I can do this." But it's in 3 days, okay? It's like 3 days before the semester started. I got this new prep because I've never taught this class before, and I have never taught this class ever after. So it was only for that one semester that I taught that class. Okay, so the comment from Andre is, doesn't CISP 400 go over everything? I'm not sure, 40% of what class? Well, okay, so the difference between 401 and 400 is 401 is Java and 400 is C++. The difference is one, okay, there are many differences, okay? One of the main differences between Java and C++ is C++ has pointers. 400, Java does not use pointers, it uses references. They are sort of the same thing, but also at the same time, not really the same thing. Pointers can lead to a lot of headache, but in this class, in 310, we are only using pointers, right? We are not using references. And that's why the prerequisite of this class is a C++ class, and for people who took Java or Visual Basic, it's not gonna cut it. So just want to make that point. Yeah, 400 is not really the same as 360. 360 is supposed to focus on control structures, the basic stuff like arrays, pointers, and so on and so forth. 400 should focus on object-oriented programming. So we're talking about classes, inheritance, virtual methods, pure virtual methods, and so on, polymorphism, that sort of stuff. That is what 400 is supposed to focus on. 360 is supposed to focus on control structures, like if then else, for, while, do while, that sort of stuff. So there are supposed to be differences between those two classes. All right, so are there any questions about the code that we explored today? Or the technique to double check whether the code is working or not? Or the understanding of what is supposed to happen on the stack as this program executes? I know I'm asking a lot of questions at the same time, but I want to give you guys some prompts of what might be some of the questions that you have at this point. I'm not seeing any questions. Let me ask this question instead. How many of you feel comfortable with recursive functions? Given the function is given to you, that you are not the one who has to write the recursive function, just to understand how it works. Okay, good, good. Okay, 6 out of 10. Okay, so if you're not comfortable with recursive subroutines to begin with, you might want to use GDB to gain insight to how it works in C++. Because the worst thing that can happen is not really understanding what the C code is doing and then try to translate that into assembly code. That is kind of like, having Google to do translation, or worse. Okay, so the first thing you need to do is to understand what the C code is doing, and once you have a thorough understanding what the C code is doing, then it makes sense to start the process to translate into assembly code, because you kind of need to know really understanding what the C code is doing first before you can do the translation, because otherwise you can't debug the code in assembly. All right, so to answer my own question, we're going to do it. Okay, we'll go ahead and compile the C code. Okay, so let's see. I'm just going to specify the executable to be the same name, and here's the source code. Of course, I missed a semicolon because I have been writing a lot of code in JavaScript, and in JavaScript, the semicolon is quote-unquote optional. Some people say religiously that you have to do it, and other people say religiously that you should not do it. So I don't do it because I'm lazy. All right, so there we go. GDB string length. There we go. And one thing you should do is to put a breakpoint in the subroutine itself, which is text string length. And then when you run the code, every time it gets to the entry point of the subroutine, it will give you a breakpoint, right? So this is the first time we call it. And that seems to make sense because the entire literal string recursion and the exclamation point is the argument. And this is the first time it is called. This really is just the the actual address in memory space. But it's kind of useful to keep track of this one. Okay, so we'll keep an eye on this. Continue execution, and now this is the recursion. This is the second call to text string length, and this is the first recursive invocation. You can see how the string is instead of at the address ending with 4, it is now at the address ending with 5. And you can also see, in terms of looking at it as a literal string, it is no longer recursion. Instead, it is ecursion, because the R is not pointed to by this pointer anymore. We advanced the pointer to point to the next character. And then we keep going, going, and this is our last invocation. So in the very last invocation, the pointer, the parameter, is pointing to the null character in the string already. So at this point, it will return a 0, and then it will basically go back to the previous invocations. So if we were to single step, let's see, where is it located? It basically says we're on line 6, but I'm not really sure, whether it returned or not. Okay, so this is where BT or backtrace is going to be helpful, because when you type BT or backtrace, this is what it looks like. Okay, we are currently at frame 0, which is the most recent invocation. And at that most recent invocation, the string, the parameter, is pointing to the null character of the original string of recursion exclamation point. And we can also see all the previous invocations. They're all quote-unquote stacked up on the stack. Okay, and this is how it is going to be helpful to understand how this code works. So if I single step one more time, it's going to go back to the previous invocation. So when I do BT, if we have one fewer invocation now, because you can see the current invocation is no longer displaying the empty string, which means PTR is pointing to a null character. Now it's pointing to the exclamation point, which is the second. Depending on how you count it, this is the okay. The best way to describe it is this is the character before the null character. So if we single step again and do a BT, it is now going back up a little bit more. So this is how you can kind of keep track of how the subroutine works, how recursion works, and how it is using the stack to kind of keep track of its own parameter for each invocation. It needs to keep track of its own parameter. Does that help? I mean, is this helping? No questions? Alright, so let me release the lab for tonight first, and then I'll give you guys the a really long and spelled out version of this code so that you can actually track the change of values of variables and whatnot. So first thing first, I'm going to release the assignment, the lab first. Alright, so the lab tonight is called function calls, and there are two components to it. One is in the quiz format, and that one is due tonight at 8:20 p.m. And then the other one is due next Tuesday at 5:30 p.m. So let me release the first one first, because you kind of have to dig through the quiz version first in order to kind of get there's a lot of repetition, in this particular lab compared to what I actually talked about in the lecture. The passcode is swap. I'm going to put that in the text channel. Swap is the access code of the lab, and it is due tonight. So it's July 15th, 8. I will give you guys a minute. I'll give you up to 8:22 just to kind of, because I keep talking at this point, you cannot start. Okay, there we go. Alright, so this is the lab portion that you have to do tonight, and then we'll go back to the portion where it is due next Tuesday. But I would definitely not procrastinate on this one. It's probably a good idea to work on this like further tonight if you have the time, even though it's not due tonight. The assignment, which is where you submit the file, has no passcode. So let me use the calendar instead to specify next Tuesday, which is the 20th. And we'll make it due right before class, which is 5:30 p.m. The reason why I make it due right before class is because I don't want people to spend the lecture time to continue to work on the program. So, that's why it's due right when we start the lecture. There we go. Alright, so now you have all the activities released, and you can get started with the lab portion. And I'll go ahead and make a zip file out of the two files that I worked on today and post it in the text channel, so that way if you want to have a copy of those two programs, you can have those, because that might be helpful from the perspective of understanding the concepts. There we go. Alright, so I just uploaded the zip file that contains the source code of both the C and also the TTP ASM. They work out exactly the same way, so that would be I think it's going to be a good reference to use. Plus, the trace analyzer will work on this one too, so. Alright, so I just uploaded the zip file that contains the source code of both the C and also the TTP ASM. They work out exactly the same way, so that would be a good reference to use. Plus, the trace analyzer will work on this one too, so. Alright, so I just uploaded the zip file that contains the source code of both the C and also the TTP ASM. They work out exactly the same way, so that would be a good reference to use. hopefully you can use the trace analyzer to kind of visualize, how this program works. Alright, so if there are no additional questions, I am going to stop streaming to YouTube first, and then stop streaming